To recap some of the last videos that we saw in this series for lecture 19, we set up a basic linked list. We set up each link separately with names for everything. We then set up functions, standalone functions that inserted nodes. And so we used this approach, a C-style approach, where we set up standalone global functions. We use structs with everything public, and then we transform that code into a class, a linked list class with private member variables and accessor mutator functions. The book does it a little bit differently. They set up a class for the nodes, the actual node itself. They set up classes, and so I'll go over that. You could just as well do that to convert our struct to a class with private member variables. And then what we did was we created a linked list class, which if you look in the book, it doesn't actually do that. They don't do it for a singly linked list, but they do it for a doubly linked list. Okay, so I'm gonna maybe not go that much into detail with doubly linked lists here. I'm gonna assume that you're gonna read the book and see compare our singly linked class that we set up in our previous couple of videos with what the book does. And then we took it a step further. That is, not only did we create a linked list class, we templatized it, and we saw how easy it was. Well, it was a simple class with just a couple of methods, and so it wasn't very hard at all. It just took, takes less than 5 minutes to templatize that simple class. And then later on, we'll use friend classes. So for linked lists, just steps 1 and 2. Even there's so many options to do things. So we went over all of this. We saw how to set up a simple list node struct. In the case of the example that's in the book, there's 2 data members in addition to the pointer to the next node in the list. And also they use type defs. Now I skipped over those. You can do it, but I just didn't feel like it. I don't mind seeing the node pointer everywhere, and it doesn't, it's sort of, for me personally, I like to see it. So the book takes a different approach and says that they don't like having this list node star everywhere. For me, it's not such a big problem. Okay, so in the book they type def the pointer, and they use that list node pointer everywhere. Couple of things to note here. Order here is important. That is, you could not put this type def in before the struct list node, because you need to know what list node is. In this case, it's a struct. So list node is defined first, and then it's used in the type def. There is this circularity or recursiveness in this data structure, and actually these kind of data structures are called recursive data structures. That is, normally with other things we don't see this. We don't see let's say a class or a struct of type X with a data member that's either a pointer to or the same kind of thing. Now in Java, the way this would be different is, first of all, this would be struct, this would be list node. Here you would just say list node and then link. Of course, you don't have the star. So convert this to a class, make everything private, remove the star before link, and in Java that would just mean that link is a reference data type. That's basically a pointer to list node. That's exactly what we have here. Okay, so Java, this is all doable. It's different, it's a little safer because there's a lot of things that Java does. For example, all pointers are by default initialized to null, and as we saw in some of the previous videos, it's a good idea to set up every pointer, every time you have a pointer, initialize it to null. Even if you're going to set it to something else in the very next statement, it's still a good idea to, whenever you declare a pointer, set it equal to null. Okay. So the head pointer, as we saw this box labeled head. It's not a node, it's a pointer. So in the book they use list node pointer. I just use node star head. Okay, same thing. And we could just put instead of saying list node pointer head, you could just say list node star head. That would work just as well. So head is just a simple pointer. It doesn't have anything inside it, just a memory address really. And what we will do, the convention is to use a name like head, and there's also a tail. So a list will have a first node and a last node. I like to use first and last. The book prefers head and tail. Either one is fine. So what's usually done is you initialize, and this is the kind of thing that I would do is if I wrote a statement like this, I would say head equals null right away, just to make sure that there's no chance of a bug somehow getting in. So the head is, and later on we'll have it point to the first node in the list. So the head is used to maintain the start of the list. It's also used as arguments to functions. We saw that we set up the insert function and the print function, and we had to pass in the head as an argument. How do you access the data members of a node? Here's the hard way: is you say whatever pointer, let's say head, dereference it, and you need the parentheses. If you didn't have the parentheses, this would have higher precedence, the dot operator. So you would say head.count and then star of head.count, which doesn't make any sense because this is an int. So that's why you need the parentheses around the head, star head, and then get the count data member of the thing. So the way to read this would be the thing that head points to, get the count data member. Okay, in Java we wouldn't have to have any of these. We would just say head.count. That's nice. But in C++ we have to have it's a little bit more low level. You have to worry about pointers. Okay, so you can assign values, you can print out, for example, the count and so on by using this notation. The alternate, which is what we used in the examples in the last few videos, is we use the arrow operator. This combines the dereferencing and the dot operator to access data members of a struct or a class. So instead of doing this, open paren star head close paren dot count, this is much more easy to see visually, see and understand visually. Right? This says head is a pointer, get the thing that it points to, get the count data member. And of course in Java we would just say head.count. So it's simpler, even simpler. You can write things from the console, that is from the keyboard, into head.item, or you can print it out, see out, the insertion operator, head arrow item. Do not forget about null markers, and that is one reason why I always initialize all pointers to null, is so that you don't have runaway iteration when using a linked list. So if you skip out on the null pointer for the very end of the linked list and you use some of the loops that we've used so far, for example, when we print, we say while p not equal to null. Well, the reason we do this is because we assume that the very last node will have a link data member set equal to null. Okay? And that's why this works. If we forget to set the link data member of the last node to null, this will may never be equal, and you might have runaway iteration that is an infinite loop, or maybe it'll crash the program because we didn't initialize the linked data member to anything, and maybe it might point to some invalid area of memory, and it'll make our program crash. So the two things we want to do is make sure that the end marker at the very end, use null for the next or the link data member, and this indicates there's no further links. And so check for, and then once you're sure you have that, if you're trying to process a linked list in a loop, you want to check for the null value. So this provides an end marker similar to how we use partially filled arrays. Let's say we had an array of size 10, but we only had the first 5 locations. We would check and only go up to the 5th location. So this is the same idea. Okay, so notice, however, that we only allocate enough space to store exactly what we need to store. So for example, in this set of 6 strings, if we set up an array, let's say at some point we needed 600 strings, we would have to set up an array right away to be 600, right? And so we'd have a whole bunch of, let's say, a whole bunch of strings. The way we use linked list, we could put in 6 strings in there, and we only allocate memory for 6 strings. If we want to put more later, we use more memory later. If we want to delete some of those things, we use less memory. Over here with arrays, it's fixed size. If you want something that's variable size, you want to use vectors, but even there with a vector, effectively what a vector does is it has an array internally and it doubles the size. Usually the problem with that is that, let's say you put in 1,000,000 things into an array and then you delete all but one. Well, you still have an array of size 1,000,000. Usually arrays don't go down in size unless you specifically say that you want to do that. So arrays are handy to use. You don't have to worry about coding up all these dynamic data structures. This wasn't so hard. But the nice thing about nice thing about linked lists is that you only use pretty much as much memory as you need. Of course, there is some overhead for saving links and stuff like that. But once we get to, to storing really complicated objects, let's say a sequence of JPEG images, each of which are, let's say, 1 megabyte, then we start to see that the overhead for actually creating a linked list of images is very little, it's not much at all. We have to have a node for each image, let's say, and you could do that right here. The overhead is just this pointer, essentially. Okay, so linked lists can be very efficient ways of using memory. Of course, you have to make sure that you set it up right, set up the data structure right. You want a null for the last location, for the last link, to show that you have no more links after that particular node. Okay, so if you have just structs and global functions, you can access individual data members inside a struct by saying head arrow count. You're just going to access the count data member of the node pointed to by head. You can assign it a value 12. Okay, you can take in this case, we didn't do this in the examples, but you can store, if you're storing strings, like item, the item data member is a string, you can assign it the value bagels, and you've changed this data member. So with linked list, the idea is the first node is usually called head, although in Java, a lot of the Java examples, a lot of the people who write Java data structures use the word first and last, and the book uses tail. So there's nothing that says you have to use head, but that's the convention in this book. So the first node is pointed to by a pointer named head. That's technically how you describe the first node. The last node is also special. You can think of the member pointer variable set equal to null, and this is an easy way to test the end of a linked list. And often what's also done is, just like you have a head data member for this linked list class, you can also have something like this. And we will do this for certain cases. We will say tail. And so that would be a quick way to get to the end of the list instead of having to use something like a loop, that's the only other alternative.